So let's get started. Today we are going to talk about the exact inference, and in exact inference we have only one algorithm in our syllabus, that is variable elimination algorithm. So we are going to talk about it today, and you will find it interesting also. So yeah, let's get started. Okay. So when we were talking about, in the previous lecture I talked about, right, that is inference, probabilistic inference. So there are two types of inferences that we have. One is our exact inference and other one is your approximate inference. So first we will be talking about, in this lecture we will be talking about exact inference, and then in the upcoming lectures we will be talking about approximate inference, where we use sampling. Okay. So let's see what is exact inference and how we can use variable elimination algorithm for that purpose. Okay. So there, when we a Bayesian network is given to you, so we have already covered the Bayesian network. So when given a Bayesian network, what questions we might want to ask? So you can say that one type of question can be the conditional probability query, right? That what is the probability of X given E? So this type of query can be asked using, if a Bayesian network is given to us. What else? We can also ask these type of questions, maximizing or maximum posterior probability. That means if we want to find out for every X given E, we can find the probability and we can find the argmax. That means we can find for X is equal to X1, X2, X3, and so on up to Xn. We can find which value of X is having the maximum probability given E. Yes or no? These type of questions can also be asked. But if I ask a general question here, that what is the whole probability distribution over variable X given evidence E? So these type of questions, if I have these type of questions, then what we can do for such type of questions? So basically we know that in these type of questions, what we can use simply the joint distribution. Yes or no? Because what is the question? Question is, what is the whole probability distribution over variable X given evidence E? So for that purpose, we have to use the joint distribution, right? And we know joint distribution is very powerful because we can answer every question related to a domain, right? Using the joint distribution. So to answer any query involving a conjunction of variables where we have multiple variables, sum over the variables not involved in the query. So if I say that if we are using the joint distribution, if let's say we are finding, this probability of D. So can I say that if I have four variables, A, B, C, D, I can write like this? So what we are doing? We are doing the sum over remaining variables, that is A, B, and C. Okay. You will understand it. You will understand it in some time when I'm going to take the example of that. Okay. So what we are doing then, let's say we are finding the probability of D. So we can say that it is equivalent to summing over all the remaining variables, that is A, B, C, and we can write like this. And this is same as writing separately also. That means summing over A, all the values of A, summing over all the values of B, summing over all the values of C, where A is equal to, let's say, small a, and B is equal to small b, and C is equal to small c. So we can write like this also. And further, if I talk about any conditional probability, let's say probability of D given B, we can write like this. These are all the expressions that we already know, right? This is nothing but the conditional probability of B comma D, that means B intersection D divided by probability of B, right? And we can also represent this in this way, where whatever hidden variables we have. So in this case, if I'm finding the probability of B comma D, then can I say the remaining variables A and C are my hidden variables? Yes or no? And if A and C are my hidden variables, I can write like this, that summation over A and C, and then probability, or you can say the joint probability distribution over all the variables. Yes or no? Correct. Similarly, and divided by, here the hidden variables, if I'm finding probability of B, then hidden variables will be A, C, and D, and I can write like this, right? So this is not difficult. This is very simple. Now let's take a simple case, and now you will understand it, easily. So let's say this is the Bayesian network given to you. If this is the Bayesian network given to you, and if I simply ask you one thing, that what is the probability of, let's say, A comma B comma C comma D, then what will be your answer? You will simply say, sir, we now understand what is Bayesian network. So the joint probability distribution for this Bayesian network, we can write like this: probability of A multiply probability of B given A multiply probability of C given B multiply probability of D given C. Yes or no? Based on the concept of Bayesian network, can we say we can write like this? We already know this, correct? You can also write like this, that in probability of A multiply probability of B given A multiply probability of C given B comma A. But we can use the Markov property also. That is the reason. And what is the Markov property? We say that probability of the current next state will only depend on the current state, which is B here, not A. So that is the reason why we write like this. Okay. So we can say here that if I want to find the probability of D, because this is my final state, right? D is my final state. I want to find the probability of D. So I will simply write like this. So whatever the hidden variables we have A, B, and C. So these are the hidden variables. So I will sum over all those variables A, B, and C for this joint distribution. Yes, that is correct. We can say so, right? So we are going to sum over all the variables, hidden variables, that is A, B, and C, and we can write this distribution like this. And further, you know that this is just, now we have written it. So instead of writing this joint distribution, we can also write like this. Any doubts so far, Abhas and Gurudeep? If you have any doubt, please ask. Clear so far? Okay, nice. So instead of writing this summation over A, B, and C, can I distribute it? Can I divide it into multiple summations? Yes, we can do. If we have three variables, summation over three variables A, B, and C. So instead of that, can I say I can write like this? Summation over C, then summation over B, then summation over A. Now you may be thinking why we are, here it was A, B, C. This was the order. Why we are writing like C, B, A? You will understand in some time why we are doing it, right? But this is for sure that we can rewrite this one as this, correct? Now what we are trying to do, now carefully see this, what we will do, we can further reduce it, or you can say we can rewrite this as, see what we are doing for this, focus on this particular summation over A. Where do we have A? Now you will say, sir, we have A in these two terms, right? In these two terms. So can I say that I can take this summation over A to the rightmost part, right, where A is involved? So what I'm saying is I can write like this. This A I can take over here. Now summation over B. So where do we have B? We have B here. We have B here. So can I say I can take this summation over B to this place, just before probability of C given B? Why I'm doing so? If you carefully observe, summation over A, do you have any term A here? No. Do you have any term A here? No. Do you have any term A here? Yes. So what I'm doing is I'm taking this summation over A just before this one. Clear? Similarly, summation over B, where in whichever term we have B, we are going to place just before that. So what we have done here, we have placed this summation over B just before this one. Okay, and then we have this simply summation over C. Is this clear so far? How we are rewriting this? Any doubt here? Simple, right? Okay, fine. So as of now, we are seeing this simple examples, right? Through this example, as we are proceeding, you will understand in some time that we have understood what is variable elimination algorithm. Just by following the examples, you will understand that we have covered the variable elimination algorithm. Okay. So, and we will see, we will go to the insight of it, that why we are doing it, what is the benefit of it. You will understand each and everything. Just follow whatever I'm explaining here. Okay. So I hope this part is crystal clear to you till this part, right? Now let's proceed. Now this part, carefully focus on this part, what it is actually, what this part is actually. So if I say that all these variables A, B, C, D, these random variables which you have in a Bayesian network, let's say these are binary variables, right? Either they are having, let's say for, if I talk about a random variable A, so let's say for A, maybe it can take the value A1 or it can take the value A2. Similarly, if I talk about, let's say B, so B is also a binary random variable, or you can say preposition random variable. So I can say that either it is taking the value B1, or it is taking the value B2. And the same applies for C and D as well. So now carefully observe this term. Carefully observe this term. Summation over A, probability of B given A into probability of A. So what this actually signifies? If you carefully observe, can I say this is going to sum all the possible values of B and A? For example, I can say that this is equivalent to probability of B1 given A1 into probability of A1 plus probability of B1 given A2 into probability of A2 plus probability of B2 given A1 into probability of A1 plus probability of B2 given A2 into probability of A2. So this is the entire matrix that we are going to get. We can add all these values to get this particular value. Do you agree, everyone? Just substituting the values of B and E. Yes or no? Just give me thumbs up in the reactions if it is clear till this point. Right? Okay, nice. So now if I proceed further, now can I say that carefully focus on this particular, carefully focus on this particular value, or I can say this, right? Yeah, let's focus on this particular row and this particular row. If I talk about the first row, so in the first row, I can say the value of B we have taken as B1, right? And for the second row, we have taken the value of B as B2. So can I say the first row entirely, I can write it as, just I'm talking about the first row, I can write it as summation of probability of B1, or you can say, yeah, you can say B given A1 into probability of A1. Can I write like this? Okay, it should be a probability of B1 given A, because we are focusing on B1, right? We are focusing on B1 value. So because mainly we are talking about probability of B given A. So A can be A1, A can be A2. So this first row I can write like this. This first row I can write like this. That is summation of probability of B1 given A, and A can be A1 and A2. So both values will be covered in this summation only, right? Similarly, the second part, I can write it as summation of probability B2 given A, probability of A. So this is what they have written like this. Okay. Okay. So given the value of A, because A we are fixing, right? For a given value of A, either the value of B is B1 or the value of B is B2. So for that purpose, we can write this in a more compact way like this. Clear? Okay, fine. Now this thing we can write it further as F1B, right? So if you carefully try to observe what we are trying to do, we know that this particular thing I can write like this. So I'm trying to basically eliminate the variable here. Now, how I'm eliminating the variable? What is the intuition behind it? Now, carefully understand. See, I'm mainly interested in finding the probability of D. Do you agree? Yes or no? Yes. So if you will say that probability of D is mainly depends on C. If somehow I can find this particular value, right, then I can find this. Yes. Let's focus on C now. If somehow I can find this particular value, then I can find this one. Correct. Similarly, if somehow I can find this particular value, then I can find this one. Why? Because B is conditional dependent on A, right? So what I'm trying to do here, I'm trying to eliminate the variable one by one. Okay. I'm trying to eliminate the variable one by one, and I'm placing it, or I'm going to keep as a factor here. That means there will be some value, but you can understand in this way that I'm trying to reduce, or I'm trying to eliminate the variable by putting the factorization here. Okay, so carefully see this, you will understand. Carefully see this term I can write like this thing is clear to us, right? Now this whole term, I'm saying that this is nothing but f1 of A. Now I'm saying that this is nothing but, let's say it is f1 of A. Sorry, f1 of B, because we are interested in finding the probability of B, right? B given A. It should be probability of f1 of B. Is this clear? Any doubt? So this entire term, I'm replacing it by this factor. Now this factor can be either the probability itself, or it can be some other value, So I'm replacing this f1 of T. At this point of time, you may be having, or you might not be having the entire clarity of why we are doing it, or how actually we are doing it, but it will make sense in some time for sure. But just let me know, is this clear so far? Are you able to follow at least something? Avas and Gurudev. Any doubt? If you have any doubt, please ask. Okay, good. So now I can write this term as like this one. So just I have replaced the entire term by f1 of B, as you can see here. Now carefully observe. Now we have a summation over B, probability of C given B, f1 of B. The same way, how we replaced that previous term with f1 of B, can I say I can now replace it with f1 of C? And you can also observe that we have eliminated A, because there is no term present in term present here which is having A here. So we have eliminated one variable from this Bayesian network. Okay, you will understand in some time that why we are actually eliminating, what is the benefit of this. Okay, but just follow this example. So this entire term I can write it as f2 of C, right? Why f2 of C? That means this is the second factor that we have, you can say that we have assumed. So we can say now this is the second factors, because the previous factor, so basically we give the numbers to these factors, okay, just to differentiate, nothing else. So here it was f1 of V. Now we have made the second factor, so it is f2 of C, because here we are trying to find what probability of C given B, so it is f2 of C, right? Or in other way, you can also understand that we are summing over B. So ultimately, if I'm summing over B, that means B will be eliminated. If you see the previous example, we were summing over A, variable A, so A will be completely eliminated, right? That is the reason why we are having f1 of B, why we are having f1 of B. Similarly here, it should be f2 of C. So now we can have this term, B is also eliminated. Now we can say we have this thing. Clear? Now this is summation over C, probability of D given C, f2 of C. Now can I say now we have actually what we wanted, right? Now we have eliminated A, we have eliminated B, now we just have C and D. So we can easily find this probability of D given C into into f2 of C, right? Is this clear? This example is clear or not? Just let me know this, the steps that we are following, right? This class is going to be more of theoretical, right? But we have one question at the end. We will see that also. Clear? And you can expect 1 mark question from this one, this particular topic, exact inference. Okay. And I will let you know what kind of question you can expect. Fine. So this is a simple example. The most, you can say the most simplest example that we have seen. So we can see this. So what is variable elimination algorithm? I will come back to this slide later on. Okay. This is the entire algorithm that is given to you. I will come back to this. As of now, you don't have to even look at this. Okay. Fine. Now let's see a more complex example. Now here you can see again, one more Bayesian network is given to you, right? One more Bayesian network is given to you. Okay. And what you are trying to find out, you are trying to find the probability of dysphonia, whatever it is. So basically for every node, whatever, like for risky visit, so we are considering the random variable as V. Here it is T, X, A, L, S, B, and D. The first letter of the word of random variable, right? Just to denote it in short notation, nothing else. Okay. So let's say we are trying to find this probability of dyspnea. Okay. So if I want to find this probability of D, let's say in short, probability of D. So again, if I have to find this joint distribution, if I have to write this joint distribution, how can I write this? Let's write it here, and then we will verify from the next slide. So can I say, let's start from this one, probability of V. So I can say it should be probability of V multiply, it should be probability of T given V multiply, it should be what? Then it should be probability of A given T and L, correct? A given T and L into probability of L given S, then probability of B given S, yes, and yes, then we have this probability of X given A multiply probability of D. Okay, probability of S we can also have. Okay, I can write like later, or let me write it here. Probability of S, and at the end we can have this probability of D given A and B. Is this clear? This thing you already know how to write it. In the Bayesian network we have already covered it. Any doubt in this expression? This is the joint distribution that we are writing for this given Bayesian network. If you have any doubt in writing this, please ask, or you can just revisit the lecture that we have already seen, that we have already covered, Bayesian network. I hope it is clear. Okay, so now this is what we have. So in order to find this probability of D, so I have to include all the hidden variables. So carefully see this probability of D. So this should be the we have to take the sum over all the variables that we have. So we have A, B, I hope it is visible, A, B, J, T, S, X, and V, right? And this is the expression that we have already written on the previous slide. You can match also. This is exactly same. Okay. So now we will do what? Variable elimination on this graph using elimination order. So this is the elimination order that we have decided. Okay. So it depends. See, elimination order also matters. Understand this thing. What elimination order you are deciding, that will also, you can say it, the number of factors that you are going to get also depends on that. We will see that what are the properties of variable elimination algorithm at the end. But understand this point, or you can write somewhere also that elimination order matters in this particular algorithm, variable elimination algorithm. Okay, so for this particular example, let's say this is the elimination order that we have decided. Fine. Now, and mainly you can just see that how we are deciding the order. So you can see that whatever variables are free, or you can say they are not dependent on anything. So you should try to have those variables first, right? You should sum over all those variables first. So it's like that, but it is not fixed. This pattern is not fixed. So there can be many elimination order that can be possible. Okay, so let's proceed now. So what we are doing, carefully see this. So we have what? Probability of t given v into probability of v. So what you are going to do, let's start with v. Let's start with v. So sum over v, can I say I can have sum over v here? Because in any other term, v is not there, correct? So I can start from here, summation over v, probability of t given v, probability of v. And I can write it as f1 of t. I can write it as f1 of t. So directly I can say I can write it as f1 of t. So can I say the variable v you have eliminated completely once you place this f1 of t here? Yes or no? The same thing we are following. Okay. So this is what we have now. Now what is next? Let's say the next variable we are picking is x now, based on the order that we have decided. V is done, now x. Okay. So x is involved here. X is involved only in this probability of x given a. If you see in any other term, x is not there. Can anybody tell me what should be the value of, if I simply ask you one simple thing? If I simply ask you one simple thing, probability of x given a, summation over x, can you tell me what should be the value of this? Think about it. Very good. That is absolutely correct, Gurdeep. If you can recall this thing I've already covered in the initial lectures. So this is very simple concept. See, given a, so a is fixed. It is given already. So a is fixed. So if a is fixed, what can be the possible values of x? Either x can be, let's say it is a binary variable. So either x is false or x is true or x is false. Yes or no? So I can say this is nothing but, you can rewrite this thing as probability of, let's say x is equal to true given a, right? Plus probability of x is equal to false given a. And these two terms, the sum of these two terms is nothing but 1. If you remember, these things I've already covered in the prerequisites of this uncertainty topic. Yes or no? Correct. So this is equal to 1, right? So now I can directly just replace it, this one. I can replace it with 1. So we have this one, and that f1 of t, we have placed it here. So now this becomes 1. So you can just ignore it or remove it. Now what do we have next? S. So for S, we have, carefully see this, S is present over here, S is present over here, S is also present over here. So can you see this? Let me just add one slide here. It is something like this: probability of B given S into probability of L given S into probability of S. If I sum over it over this variable S, now what kind of factor I can write here? Can I say, as we are summing over S, whatever remaining variables you have in this expression would come under this factor? So let's say if it is factor of, I think 2, right? So factor of 2, can I say I can write this as B comma L? Do you agree? Yes or no? If I'm summing over this variable X, whatever is the remaining variables, I can write like this: factor 2 of B comma L. So now what we can do is, we can consider this term entirely and we can replace it with factor 2 of B comma L, factor 2 of B comma L, right? So I can write this now like this. Now we have this thing. Now the next variable we have is T. So T is present where? In these two terms, T is present. Now carefully observe. Already we have one factor term, F1 of T, and we have probability of A given T comma L. I have probability of A given T comma L into F1 of T, and we are summing over this variable T. Now, what can I write? What do you think? What should be the next factor? Let's say F3. What should come in this factor? whatever is the remaining variable, because you are summing over variable t. So whatever is the remaining variable, it should be, can I say it should be a comma l? These two are the remaining variables, right? A comma l. Yes or no? So it should be a comma l, f3 of a comma l. So now I can write like this. So can you see in every slide we are trying to, whenever we are summing over any given variable, we are basically eliminating that variable from the Bayesian network. Carefully observe. Initially we had this one, right? So v was gone. Now we don't have v in the Bayesian network. Then we summed over this x. So x-ray is gone. Then we summed over this s, that means smoke. So smoke is gone, right? Then, and now here carefully see, we have f2 of b comma l. So there will be one edge between b and l now, right? Once we make this factor, so there is edge between b and l. Smoke is gone. Now after that it should be factor 3 of a comma l, a comma l. So, and t will be gone. So t is gone. Now there is a edge between a comma l, right? So far this is what we have got. Okay. Now next variable is l. So I can sum over this variable l. So, and these two terms are having l here. So can I say I can make a new factor now, f4, and that should have the variables b comma a or a comma b, you can say. Yes or no? Because l will be eliminated. So this is what we are going to have, f4 of a comma b. So once you eliminate this l, now you place this here, there will be one link between a and b here, like this. Is this clear? Any doubt so far? Now what should be the next thing? The next thing is a variable b. So now we are going to sum over the variable b, right? So variable b is present over here. Can I say I can make the new factor now, f5? Yes, we can make the new factor now. And what will be the variable present in that? So only the variable, if I'm summing over b, a will also be present, right? Okay, so actually as we are finding this probability of d, so we can ignore this d, because ultimately we are finding this d given something, right? So when we are summing over this b, so ultimately we are going to have just f5 of a. That means whatever variable remaining apart from d, because we are already finding this d, right? So apart from d, so we can have this f5 of a. So once you place this f5 of a, so you are summing over b, so this b will be gone from the Bayesian network, and you have just this one, and this is what is the final one. So as you can see here, finally, to get the probability that variable d has a value little d, what you have to do ultimately, you just simply sum factor f5 over all values of a, and that will give you the probability. Are you getting this point now? How this algorithm is helping us by eliminating the variables? Yes or no? In some time you will understand it more clearly. You will gain more insights how this is actually helping us. Okay. Is this clear so far? Shall I proceed now? Fine. Okay. So now the question is, why use the variable elimination algorithm? What is the benefit of this? So one reason for constructing a Bayesian network is to calculate probabilities. Yes, there are many probabilities that we may want to calculate. Exactly true. For example, the Holmes scenario. See, this Holmes scenario is same as, if you remember carefully, we saw one Bayesian network where we had the burglary, earthquake, alarm, John and Mary calling, right? That diagram. And this is same as this Holmes scenario also, just the name are a little different, nothing else. Okay, we will see that. So for example, for this Holmes scenario, we may, if we doing sum over that variable, it is equivalent to same, so it's independent of it. Abhas, sum over that variable. Okay, any variable you are talking about, if I'm summing over that particular variable, it is equivalent to same. I didn't get your point. What equivalent to same means? What? If you are summing over any variable, that means you are adding all the values of that variable. If you are adding all the values of that variable, if you have added all the values of that variable in that particular factor, so you can say that you have removed that variable, right? Yeah, it becomes independent of it. D not make any sense because actually D D was depending on A, right? D was depending on B and A mainly. We eliminated B, and then now we have just one variable, that is A. So that means in order to find probability of D, you can just sum over this factor of A, right? And that will give you the value of D. That is the reason why we are not writing D on the right hand side explicitly now, because all we have is now just this single variable A. If you go back to this slide, see, what do we have here? We have summation over A, summation over B, probability of D given A comma B into F4 of A comma B, right? Now first we are doing summation over B, so we can remove B, right? So ultimately you will be having this thing only. If you remove B, you will be having this thing, right? A, and here it should be D, correct? And this is nothing but probability of, you are finding probability of D. So can I say, if you just, because D is conditional dependent on A, so if you just sum over all the possible values of A of this factor, you will be getting the value of D only. Yes or no? Because D is conditionally dependent on A. Is it clear or not? Because just see, this is a factor. This is not the exact probability. Sometimes it may be exact probability, sometimes it may not be. Okay. We will see this once we have one question, you will understand it. Okay. Fine. So now let's say this. So for example, this Holmes scenario, we may want to calculate the prior probability for the alarm to go off without knowing anything else. Also, suppose one day both Watson and Gibbon call Mr. Holmes. That means in our previous example, if you remember that example, John and Mary were calling, right? So let's say here it is Watson and Gibbon, they call Mr. Holmes. Given both calls, Mr. Holmes, we may want to calculate the probability that a burglary is happening, right? So these type of questions can be asked, right? So now we will see, let's consider this example and we will see why we can use this elimination algorithm and how it can help us. So this is the Bayesian network given to you. And as I told you, in the Bayesian network, you have the graphical model. Apart from that, you also have the CPTs, conditional probability tables. We already know this, right? Now, suppose that we want to answer this particular question. Let's say you have something R also. Here it is not mentioned exactly what is this R, but let's say some other variable is also present over here. B stands for burglary, E stands for earthquake, A stands for alarm, W stands for Watson, G stands for Gibbon. There is something, one more variable that let's say it is R. Okay. Now suppose that we may want to answer this question. Now this is the question that we have. What is the probability that a burglary is happening given that Dr. Watson and Mrs. Gibbon both called Mr. Holmes? So this type of question, if we have to answer these type of questions, then this seems like a question Mr. Holmes would want to answer. And to answer this question, we need to calculate the probability of burglary given Watson and Gibbon called. Both are called. That means ultimately, can I say that I'm interested in finding probability of burglary given Watson and Gibbon? Yes or no? This is ultimately we want to answer in this question. Correct. Now you know how we can write this. Now you know how we can write this value. This value is nothing but this value, probability of B given W comma G. You can say, we can write this as probability of B comma W comma G. And here it should be what? It should be probability of W comma G. This is nothing but the total probability. We already know this. So can I say this is same as probability of B comma W comma G divided by probability of B comma W comma G plus probability of not of B comma W comma G. Yes or no? Is it clear or not? So the same thing they have also mentioned that we are interested in finding this probability. All these things you can just give it a read. So B is a query variable for which we are making a query. W and G are the evidence which is given already, observed values you can say, and any other values, any other variables which are not present in this expression are your hidden variables. So A, E are your hidden variables since they do not appear in the probability above. So I can simply write, just now I've written this, and this is nothing but this thing only. The denominator that we have is nothing but the total probability. We already know this concept. Fine, let's proceed then. Now let's focus on this value, the numerator, probability of B and W and G, which is a joint distribution. Now to find this joint distribution, if I sum over all the variables okay, as it is mentioned also, carefully see this, given our derivation so far, calculating this is equivalent to calculating the joint probability of this, right? Because ultimately denominator we can always find, right? Now this joint probability does not contain all the variables. As you can see, this thing does not contain all the variables, only 3 variables are there. So we cannot calculate it directly using the Bayesian network yet. Are you getting this? And you can also find this, like if you carefully see it, if you don't have all the variables involved, if you see this diagram also, you will see that if all the variables are not involved, you won't be able to find it directly using the Bayesian network. Okay, so let's introduce all the other variables into the expression. So A, E, R are your hidden variables, so we have included those variables also. Now again, when we are introducing those variables, we will use the sum rule in reverse and introduce these hidden variables E, A, R. Okay, so you can see this expression that, now carefully see this, in this variable elimination algorithm, what we are actually doing, we are introducing the hidden variables, and for those hidden variables we are writing the summation rule, that is for EAR. These are the 3 hidden variables, right? Each term in the sum is a joint probability over all 6 variables. Clear so far how we are writing it? And now using the Bayesian network, so once we have the joint distribution, now this is your joint distribution, right? You can always write like this. You know how to write it based using the Bayesian network, the graph, right? You know how you can write it, probability of B into probability of E, probability of R given E, probability of A given B and E, probability of W given A, probability of G given A. This thing you can always write using this particular graph. We know how to write it also, right? Is this clear? Any doubt, anyone? So now we have this expression. Now, if we have this expression, what we have seen in the previous 2 examples, we basically place the particular, let's talk about this first summation over R. Where do we have R term? You will find that R is only present in this particular term. Yes, R is only present in this particular term. So we can keep these terms on the rightmost side. So if I keep this term on the rightmost side, so what we can have, I will be having something like this. Where it is? Okay, they have not mentioned it here. Okay, they will say it later. Okay, they will explain it later. Now let's say, before just proceeding towards that also, now you will understand why we are actually using it and what is the benefit of using this variable elimination algorithm. So far we have this thing. Still we haven't used this algorithm, right? We are not eliminating so far. If let's say just this expression is given to us, if this expression is given to us, now these type of question can also be asked to you in the GATE exam. How many addition and multiplication operations do we need to perform to evaluate the following expression? This is the same expression that we have seen just now. So what do you think? How many addition and multiplication operation do we need to perform? Any guesses? Any idea? all variables are binary variables here, binary random variables. Before this one, just let me give you a simple example. Just tell me this thing. If I'm writing something like this, let's say probability of maybe A given B. Carefully see this, everyone. Probability of A given B. I can write this as probability of B given A into probability of A divided by probability of B. Bayes theorem, nothing else, right? Now, if I sum over, let's talk about this numerator, because this numerator is nothing but probability of A comma B, right? This is nothing but this thing. So if I, let's say, sum over all the values of, let's say, B, and we have this thing, probability of B given A into probability of A, then can you tell me how many addition and multiplication we are going to do here, we are supposed to do here? Now think about it. This is a simple example. Can I write this as, see, we are summing over B, right? B is a binary random variable. That means can have two values. So can I write like this? Carefully see this. Can I write like this? Let's say when B value is 0, given A into probability of A plus probability of B equal to 1 given A into probability of A. Do you agree or not, everyone? Just tell me this thing. Do you feel that we can write like this? This expression is same as writing this expression, everyone? Correct? How many addition we are doing here? Only one addition we are doing here. And how many multiplication we are doing here? 2. Correct? So 2 multiplications and 1 addition. If I ask you, let me just extend this question. Let's say here in this case, I told you B is a random variable, a binary random variable. If I simply say that B can have 3 possible values, let's say 0, 1, 2. Can you tell me how many multiplication and addition will be possible in that case? If B can have 3 possible values, 0, 1, 2. In that case, you are just going to extend one more addition here and you will be writing probability of B is equal to 2 given A into probability of A. That means, can I say 2 addition and 3 multiplication would be there in that case? 3 multiplication would be there and 2 addition would be there. Yes or no? Correct? Because in this case, what we are doing, when we can have two values possible, here it is 2 multiplication and 1 addition. See, these questions are not very important, and these finding the actual count is also not important. What important is how this algorithm is going to help us to reduce these operations. Okay, so just I'm giving you a normal clarity of how we can find these number of operations. I hope this is clear with this simpler example. Any doubt, anyone? Gurdeep and Abhas. Let me know if you have any doubt. I'm giving you a few seconds. Just carefully look at this slide, and if you have any doubt, please ask. I hope it is clear, right? Okay. Now let's come back to this particular slide again. As I told you that multiplication, finding the exact multiplication is not important at all. Important is just to find out the range What will be the number of operations, the addition and total addition and multiplication operations that we need? So here, if you carefully see, and you don't have to write the entire expression also, just understand this point. Here, if you see how many, we are summing over three variables. We are summing over three binary random variables. That means how many values will be possible? How many combinations will be possible? If I have three random variables, binary random variables, can I say 8 values will be possible? Exactly. How many multiplications you are doing over here? How many terms you have here? I mean, how many multiplication between these terms you are performing here? 1, 2, 3, 4, 5. 5. Are, Abhas, carefully see this. How many multiplications you have in this entire expression? 5. Correct? Okay. So 8 combinations and 5 multiplications, right? How many multiplications, total multiplications would be there? 8 into 5, can I say 40 multiplications would be there? Gurdeep, carefully see here, everyone. 5 multiplication, right? 1 between these two, 1 between these two, 1 between these two, 1 between these two, 1 between these two. 5 multiplications are there. 8 combination of random variables will be there. So 8 into 5, 40 multiplications would be there in total. How many additions would be there? Can I say 7 additions would be there? Because if you have 8 combinations, just one less than that number of additions are there. If I have 2 combinations, 1 and 2, how many addition we are performing? Just 1. If I have 3 values, how many addition we are performing? 2. So can I say 7 additions would be there here? So can I say total number of operations, including addition and multiplication, would be 47? Do you agree or not? Is this point clear? Correct. And here the solution is also, the proper solution is also given to you. You can just read it out here. Let's start from here. The correct answer is D. We need to perform 47 operations. And you can see here over 3. So we are having 3 nested summations over 3 binary variables. We are summing up 8 terms, right? 3 binary variables. That means we are going to have 8 terms. And in each term, we have to perform 5 multiplication, as I told you. So 5 into 8, 40 multiplications would be there. After that, we need to add these 8 terms. See, this is going to be 1 term. Then again, for another combination, this is going to be another term. So total, like this, 8 terms are there. And to add 8 terms, can I say I need 7 additions? So total number of operations would be 47. Right? This is when we are calculating the joint distribution, but we are not using any algorithm. Are you getting it point? Are you getting the point? So far, we have not used variable elimination algorithm in this example. Just by using purely joint distribution, how many operations we need to have or we need to perform here, that's what we have calculated here, that is 47. Now, let's try to answer this query more efficiently. So what we do here now, I hope it is clear till this slide, everyone. Gurdeep and Abhas, any doubt? Crystal clear? Shall we proceed now? Okay. Now let's try to answer this query more efficiently. So we had this expression, right? Now what we are going to do, we are going to take this summation over just that particular term where we have that variable present. Okay. So can I say, I can write first this one like this, summation over R, and I know that R is just present in this probability of R given E. So I can take this here. Similarly, summation over A, where do we have A here? We have A here, we have A here, we have A here. So I can write like this. And what about E, summation over E? So we have just this value. So even probability of B, I can write outside. Correct? Now, if I ask you the same question, is this clear how we are rearranging them? Fine. How we are rearranging them. And again, the same thing. what should be the value of this one, everyone? What would be the value of this one? It is nothing but 1 only. We have seen it already in the previous examples, right? So you can simply place 1 here, or you can just directly, you can say just place 1 here and it will be gone. So ultimately I can have just this one. Now the same question I'm going to ask again. So this expression is same as this one. You can compare also P of B summation over P of E, right? And then summation over A and this complete term. The question is still the same. How many addition and multiplication operations do we need to perform to evaluate the following expression? Do you want to try? Think about it. Let me know. Exact count is not required, just the range you need to find. Yes. 11 to 20. Okay. What about you, Gurudeep? What do you think? Same? Yeah. So that is correct. Carefully say this. So we need to perform total 14 operations. How? Again, the same thing. For the inner sum, we need total 1 addition, 4 multiplications. The same reasoning. You can take the same reasoning. Binary random variable, 2 values will be possible for A. Let's say A is equal to 0, A is equal to 1. So how many multiplication here? 1 and 2. So 2 multiplication here, right? 2 random variables, so 2 into 2, 4. And 1 addition would be there. So total 5 operations just for this particular term. Correct? Then what after that? You can see here, so 5 operations in total so far. Now for the next sum, that means the summation over E. So we have 1 addition plus 1 multiplication plus 5 operations into 2. So carefully see this, how we are doing it. See, E is also a binary random variable, so 1 addition would be there. So that is the thing why we are having this 1 addition over here. Then 1 multiplication is there. Carefully see this. This is the 1 multiplication. And for this inner one is having how many operations? 5, right? 5 operations in total. And then you are going to add again, and there also you are going to perform 5 operations again. So that is the reason it is 1 multiplication plus 5 operations into 2. Are you getting it? This entire thing, let me just denote it like this. This entire thing, as you are summing over E, this entire thing will be added twice because E is equal to 0, E is equal to 1. So once if you add this plus again when E is equal to 1, then again you are going to add. Inner operations are taking 5. So 2 into 5 plus 1 this multiplication also, right? So that will give you what? That will give you 13, right? So 5 plus 1, 6 into 12. 6 into 2, that is 12. And this 1 addition that you have for the major one, right? For this one plus again this one, this value. I hope it is clear, right? Any doubt, anyone? Even you can just write the full expression also just to have more clarity. Fine. So total 13 operations here. So finally we need 1 more multiplication. If you carefully observe, this 1 more multiplication is needed into P of B, and that will give you total 14 operations. So can you carefully see here, when we are using this variable elimination algorithm, by summing over, by placing this summation over at the correct place, and then performing this, evaluating this expression, reduced the number of additions and multiplication operations. Are you getting this point or not? This is the actual thing that you can observe here. Why we are using this? Because it helps us to answer the query more efficiently by reducing the number of additions and multiplication operations, right? So that is the reason you can see the number of operations have been reduced from 47 to 14. Clear? And again, they have also clearly mentioned that the exact number is not the point here. You should understand what is happening here. That's all. Exact number, they are not interested. Okay. So just give it a read to this variable elimination algorithm. Just read this. You can just read these 3 paragraphs later on. But carefully see this. The variable elimination algorithm uses dynamic programming, storing intermediate calculations, and exploits the conditional independence present in the Bayesian network. At a high level, the variable elimination algorithm first defines factors. At a high level, you will see now that it defines the factors. And we have already seen, right, in the previous examples, when f1 of a, f2 of something, f3 of something. So those are nothing but the factors. And then we perform the operations on these factors also. And what kind of operations we are performing? Carefully see this. Restrict, sum out, multiply, and normalize to make the particular inference. Now we are going to talk about these particular operations that we perform on these factors. And let me tell you one thing. What I feel is, from this particular topic, exact inference, if they are going to ask any question, it would be of 1 mark for sure. Because 2 mark question, they will not, they are not going to frame it, because that will take, because a lot of calculations will also be involved. So that is the reason they may ask you 1 mark question. And what type of question? One thing is maybe the way we have solved that addition and multiplication, the range they may ask. Second type of question, now you will understand once we understand these operations that we have, these 4 operations: restrict, sum out, multiply, and normalize. So first let's understand this, and then we are going to proceed. So we define the factors. You have already seen how we are defining the factors. You can just give it a read if you want. If not, you have understood the point, like how we are defining the factors, f1, f2, f3, and so on, right? Like this here also they have given you, this is the factor. So f of e comma r. So this is the factor of 2 variables. So it is going to have, for the whatever the possible values that we can have for e and r, it is going to have the values for that, right? So this is the conditional probability distribution given to you. Now the first operation that we can perform on any factor, that is restrict. What it does, let's understand through example. See, I have kept these slides so that you can later on just read it, give it a read just once. That more than that is not required. Just once, give it a read for sure. Okay. Most of the slides are from MIT University, right? And other are from, I think, CMU or some other university, but all are from standard universities. Okay. So the best resource that I could find on the internet for this particular topic, I have included in these slides. So you don't have to refer anything else for it. And this is same for almost every lecture that I'm covering. Fine. Now carefully see this example. Let's take a look at example. So f1 is a factor with 3 variables. You know what is factor, right? Gurdeep and Abbas, now you know what is factor, right? We have already seen. Now let's see this example. This factor is given to you and it is having 3 variables, x, y, z. So for that, the conditional probability table is also given to you, right? Now we are talking about the first operation, that is restrict. Now what it does, when I say let's restrict the value of x, so when I say restrict the value of x, let's say I'm restricting the value of x as a true. If I restrict the value of x as true, I'm not going to consider all those values where the x value is false. As simple as that. As you can read here, we want to set x to be true. So I'm restricting x as true. We can do this by keeping only the rows for which x is true and deleting all other rows. That means I can just consider these above 4 rows. So once I restrict it, I will be getting this one. So once I restrict x, Can you see how I'm eliminating the variable here? If I say, let's say I'm restricting the value of x as true, then once you restrict or once you perform any operation on these factors, that variable will be gone. So now you will be left with two variables only, y and z. And where that x is gone, basically you have considered in this example that x is true. So these four rows you are going to consider, and now this table will become just this one, where you have y and z and all the values where x is equal to true. So these are the values. You can compare 0.1, 0.9, 0.2, 0.8, the first four rows. This is restrict operation. This is restrict operation. So once you perform any operation on any factor, you get another factor. Now, can I say this is f2 of y comma z? This is another factor of two variables, y and z. Yes, we can say it. Correct? We can say it. If I say let's restrict z to be false. So if we restrict the factor f2 to z is equal to false, in the next factor you will be having only one variable, which is y. That is f3 of y, you can name it. Right? So z to be false, that means you are going to consider this particular value and this particular value. So 0.9 and 0.8 will be there in the next factor. And let's say further, if I say restrict f3 to y is equal to false, that means this is the final value that I'm going to consider. Are you able to understand it? Because in the question, in some question, they will be telling you, right, what should be the value of y that you have to consider, what should be the value of x that you have to consider. This is how you can find the final value. So you will be having this another factor that is having no variable, but the final value is simply, this is just a value that is 0.8. Is this clear so far? What is a restrict operation? The first operation that we have. Simple, right? Okay. The next operation that we have is sum out. This is also very easy. So again, you can just give it a read once. Okay. Let's understand through example. So let's say this is the same factor, or I think different factor with different values is given to you. If one factor is given to you with three variables, x, y, z. Now it says that sum out. So sum out operation is similar to what? Sum out rule in probability. So we can start by filling the values combination of x and z. So here the new factor would be, so basically here it is summing out. Okay, here it is mentioned that we sum out y will disappear from the factor. When I say sum out y, carefully see this, what is happening actually? When I say sum out y, that means, now carefully see this, that means for the same, if you see x is equal to true, z is equal to true. As you are summing out y, so x is equal to true, z is equal to true, the same combination. Do you have anywhere else? Yes, x is equal to true, z is equal to true. You are going to add these two values. Similarly, true and false. So where do we have true and false? You are going to add these two values, right? So summing out y means you are basically summing out those values of remaining variables, or you can say for the same values of remaining variables. For the same values of remaining variables. Sum out y means sum some values for the remaining variables. Same values for the remaining variables. Right? So you can verify also here that now you have just x is equal to true, z is equal to true, true, false, false, true, false, false. And these are the values after summing it up. So now this is a new factor that is having two variables, x and z. Is this clear? This sum out. These type of questions are possible for just for 1 mark. They may give you this table and they will simply tell you what operation they want you to perform on this particular factor. So directly they will give you the factor and they will say perform restrict operation or maybe sum out operation. So these type of 1 mark question is possible. Is this clear, Abhas and Gurdeep? Okay, fine. The third operation that we have is multiply. So again, you can just give it a read. Let's see, understand through one example. So we have two factors. One is f1 and another one is f2. F1 is having two variables x and y. F2 is having two variables y and z. Now let's multiply them together. So when I say multiply them together, it is you can say same as natural join. So I hope you remember natural join, right? In DBMS we have covered. So basically, carefully see this. Y is equal to true. Y is equal to true. What is the common variable here? Y is the common variable here. So y is true, true. So you multiply these two values. So it should be 0.1 into 0.3. That will come out as 0.03. Again, true and true. So you multiply true with true, that is 0.1 into 0.7, that is 0.07. So it is same as natural join. Then false with false. So 0.9 into 0.6, that will come out as 0.63, right? So like this, you have to okay, it should be 54, 9.6. Yeah, 0.9 into 0.6, right? Yeah. No, wait. It should be, yeah, here it is false now. Okay, fine. 0.9 into 0.6, that should be 0.54. Yes. So here you can see how we are finding it out. So 0.54 is there, 0.07, 0.03. So it is same as natural join. Is this clear? Any doubt in this multiply operation? Similarly, you can see here false. Y is false. Y is false here. So 0.8 into 0.6, it should be 0.48. So 0.48 is there. Like this, we have filled all the values. Fine. And the possible questions that they can ask like this also, that you have to perform f1 into f2 where x is equal to true, y is equal to true, z is equal to false. So first you have to find that. First you have to find this factor f1 into f2. Then from this one you have to answer this particular query where x true, y true, z false. So where x true, y true, z false, where it is. This is it is right, 0.07. Correct? That is the answer. Or directly also you can write like this. From the initial factors you can write like this also. X is true, y is true, into y is true, z is false. Like this also you can find the values. So are you getting what kind of questions they may ask from this topic? Right? And you can answer it easily. Once you know the concept, you can easily answer these questions. Right? Okay. The last operation that we have is normalize, which is again a very simple concept. This is the same idea as of normalization. So this is the one factor given to you. If I have to perform normalization or normalize on this particular factor, so can I say it is going to be 0.2 divided by 0.2 plus 0.6. So this is 0.2 divided by 0.8, which is nothing but 1 by 4. That is nothing but 0.25. You know already, you know this normalization, right? Again, where y is equal to false, it should be 0.6 divided by 0.8, and that will come out as 0.75, or you can say 1 minus 0.25 will be 0.75 here. So these are the operations that we have. Now we know what is variable elimination algorithm. Now we know what kind of operations we can perform on the factors, right? Now let's see the last complete example of this applying variable elimination algorithm to this Holmes scenario. Okay, so let's say this is the Bayesian network given to you. Now carefully understand this. So what is the problem statement? Given a portion of the Holmes scenario below, we have to calculate this. Calculate probability of B given not A using the variable elimination algorithm. What is the meaning of this? You have to find the probability of burglary given that the alarm has not set off or alarm is not going off. You have to find this. Probability of burglary given that alarm is not going off. Okay, and this is the Bayesian network given to you. Fine. So this is simple. Probability of B given A, we can, so this is misprinting here. It should be not of A. It should be not of A, right? So you can write like this. We already know this. Now let's talk about this joint distribution, the numerator part, because this is finding numerator part is same as finding the denominator also, right? These things and these things. So we can write like this. Carefully see this now, how we are applying this variable elimination algorithm further. B and not of A. Now, what are the hidden variables here? If you carefully see the Bayesian network, B and A is there, E and W is not there. So E and W are the hidden variables that we have. And for those hidden variables only, you are going to sum up, right? So summation over E, summation over W, and this thing you can all easily write using the Bayesian network. We know this, right? Probability of B into probability of E into probability of A given B and E into probability of W given A. And the same thing they have mentioned. Now they have just not of A here. So everywhere they have placed not of A. As simple as that. Now this thing, so now you can just see W where it is used. W is used only in this part. So we can write like this. And E you have in these parts, this one and this one. So you can rearrange like this. All the summation you can rearrange like this. Once you rearrange this correctly, now let's execute the variable elimination algorithm. Is this clear so far? This example is the complete summary of today's lecture, the exact inference using variable elimination algorithm. Okay, so now what will be the value of this one? Can I say it will be 1? Correct? Because given A, what will be the probability of W? So it should be 1 only. So we can write like this. Okay, they have defined the factor for this. Fine, we can define the factor for this, not a problem for us. Here they have defined the factor, so it's okay, no problem at all. Later on, maybe later on they are going to remove it. Okay, so here we have these terms: P of B, P of E, P of A given B and E, P of W given A. So we can say, as I told you, remember, sometime I told you that sometimes factors is nothing but the exact probability also. So in this case, probability of B, they have just simply mentioned F1 of B, right? So F1 of B, this is F2 of B. They have directly replaced all the terms with the factors. That is again another way to do it, or you can follow the previous method also. But okay, let's say they have defined the factors like this. So we will define each one factor for each node they have defined in the Bayesian network. And this is how the CPTs are given for the factors also. Clear? Now let's start doing it. So first of all, what we can do? So let's try to perform restrict, right? We can perform restrict because we know the value of A. For A, it is saying not of A. That means alarm is not going off. Alarm is not going off, right? So F3 can be restricted. And once you restrict F3, carefully see this, you have A here, not of A. That means A is false. That means for all these values, you will consider this and it will form a new factor, let's say F5 of B comma E. And this is how you have done it. Clear? Okay. So yeah, this is how you have done it. Now you have new factor B comma E. Now further we can see the same thing we can reduce here also, not of A. So here also not of A, that means this value and this value will come up, 0.4 and 0.6. And you can form a new factor over here, that is, let's say F6 of W, right? Are you getting it? How we are performing? When I say summation over some variable, how we are eliminating it? By performing these operations, the same set of operations. First restrict operation we are performing so that we can reduce it. Okay, similarly we can do it, and now we have this new factor list. Now we have this new factor list, which is F1 of B, F2 of E, F5 of B comma E, and F6 of W. Now what we can do is we can eliminate the hidden variables. So we can eliminate this hidden variable W. So yeah, this is nothing but 1, right? Yes, this has to be 1. See, they have explicitly mentioned it. Previously, we can just directly eliminate also, but it's fine. They have done it now. So F6 of W, now we can write that's F of 7, factor 7. And this is nothing but the single value, that is 1 only, because we know that this probability, summation over W for this probability will be equal to 1 given not of A. We know this concept, right? Fine. So now we have this thing. What we can do here, P of E is nothing but F2 of E, and this is nothing but f5 of b and d. So basically what you are doing, you are multiplying. So can I say now you can multiply, now you can apply the multiply operation on these factors. You have two factors here, f2 into f5. So f2 into f5, if you perform, you will be getting, let's say, f of 8 b comma e. So how we are getting this value, f2 of e, and focus on f5 of b and d. This is f5 of b and e, f2 of e, this is, it is here. So let's say true. So you know it is same as performing natural join. So 0.1 true. So 0.1 into 0.2, it should be 0.02, and here it should be 0.08. So the same thing they have done here. 0.9 where e is false. So 0.9 into 0.3, 0.27, and here it should be 0.81. Are we getting the same values here? Yes. 0.02, 0.27, 0.08, 0.081. Understood? Crystal clear so far? So this is the factor that we have. Now what we can do, we can sum out on this f8 of b comma e, we can sum out on e, right? Because ultimately we were performing this also, right? Summation of e was there. Carefully see this, summation of e is there, right? This thing. Once you perform this multiplication, now you can sum out, right? So sum out on e. When I say sum out on e, what needs to be done? When I say sum out on e, so sum out on e, that means wherever the value of remaining variables, for the same value of remaining variables, you are going to add those. So b is true, true here. So you are going to add these. B is false, false here. You are going to add these two values. So you will be getting 0.29 and 0.89. Is this clear? Are you able to relate everything now? Whatever we have covered. And let's say we are naming it as a new factor, which is f9 of b. So now we have new factor list, f1 of b, f7, which is one only, one value only, and f9 of b, right? So now what we have, now we can perform this multiplication only because sum out is already done. So now we have this, multiply all the remaining factors. This is one only, so you can just directly ignore also. What about this one, f1 of b, f9 of b? Let's say you are getting f10 of b. So this is what you are going to get. You can verify, you will be getting the same value. f9 of b is this, 0.29 for true. Here it is 0.3. So 0.3 into 0.29, 0.7 into 0.89. So you will be getting these values. Is it clear? Now the new factor list is just this one. Correct? Now the new factor list is just this one, f10 of b. What you can do? When you have just this value, what you can do is the final operation you can apply is normalize to get f11 of b. Once you normalize it, so normalizing is nothing but finding the final factor that contains these two probabilities. Probability of given not of a and probability of not of b given not of a. So you know how to normalize this. 0.087 divided by 0.087 plus 0.623. That will give you this value. And again, 0.0623 divided by these two values, that will give you this particular value. So we are able to find these two values clearly, right? Probability of burglary, given that alarm is not going to get off. So what is the value for that? The value is simply 0.123. Is this clear? Any doubt, anyone? So this is the final factor that you are getting. And this was the initial question, right? What is the probability of burglary given that alarm is not going to off? So this is the final value. Is this clear? Crystal clear? How we are performing this? Right? This variable elimination algorithm. Abhas and Gurudeep. Any doubt? Okay, so just let's see this last slide. Properties of variable elimination. Time is exponential in size of large factor. Yeah, if it is a huge factor, it will be exponential. Bad elimination order can generate huge factors. So elimination order matters. NP hard problem, it is an NP hard problem to find the best elimination order, right? So there are some disadvantages also. Even the best elimination order may generate large factors, right? And there are reasonable heuristics for picking an elimination order, such as choosing the variable that results in the smallest next factor. And other things are also there, but that is not very important for us, right? So I hope it is clear to you. So clearly you can read this line. When the network is such that the factors are of necessity large, if very large factors you are getting, we will have to turn to a different class of methods, which is nothing but approximate inference. And we will be talking about the next method under approximate inference, which is nothing but sampling. That is going to be our next lecture for this module, in this module. Is this clear? Any doubt, anyone? Did you enjoy today's class? This is the complete variable elimination algorithm and the topic exact inference. So your exact inference is covered. Now we will be starting approximate inference in the next lecture, and we will be having next class on Monday. Any doubt, anyone? Abhas and Gurdeep.